We've been looking at work. We've derived an equation for work, where work is the integral of PdV, and then we came up with some specific equations for work. Well, now it's time to do and heat. Heat gets the symbol Q. Q, like work, is an inexact differential. That means that it is path dependent. It depends on the process we take in going from state 1 to state 2. Heat is a form of energy, so its SI units would be the joule, where a joule is 1 Newton meter, which is equal to 1 kilogram meter squared over seconds squared. The English units for heat would be the BTU, or the British thermal unit. Now, a British thermal unit is the heat required to raise 1 pound mass of water 1 degree Fahrenheit. It's not any degree. It is specifically from 59.5 degrees Fahrenheit to 60.5 degrees Fahrenheit. And that is the definition of a British thermal unit. This may seem like something you've seen before, which is the calorie, where a calorie is the heat required to raise the temperature of 1 gram of water 1 degree Celsius. And it is not any degree Celsius, but specifically from 14.5 degrees C to 15.5 degrees C. That's just a nice little tidbit there. But getting back to heat, we can say the heat in going from state 1 to state 2 is just the integral of del Q. In some textbooks, they don't put the 1 and 2 on opposite sides. They'll put it on the same side. That's not Q12. That's the heat transfer in going from state 1 to state 2. And looking at the heat transfer, we can also have something which is the heat transfer rate. My heat transfer rate here, you can see that my dot indicating the time derivative got a little lost here. The heat transfer rate, del Q over dt, is the heat transfer rate, or the rate at which heat is transferred to or from the system. So you'll see a Q dot, that's just essentially heat per time. We can also have a lowercase q, that would be heat per unit mass. That is the heat transfer per unit mass of the substance that we have. Now it's important to note the sign convention for heat. Heat transferred to a system is positive, and heat transferred from a system is negative. So once again, heat transferred to a system is positive, heat transferred from a system is negative. In some textbooks, they'll say heat transferred to a system is heat in, and they'll say that heat transferred from a system is out, is heat out. We're going to be using positive and negative heat, but when you get to thermal fluids or some other courses, you may see that heat transferred to a system is heat in. Just a little bit more on heat. We can look at heat transfer rates through solid objects, or we can look at a heat flux. Let's consider a window. The window has an area A and a thickness X. There is a temperature gradient on this window where we've got T2 on one side and T2 on the other side. Where T2 is greater than T1, we'll have heat being transferred from T2 to T1. Another way to look at that is to look at the window on end, where you've got T2 higher than T1. That'll give you a temperature gradient. That temperature gradient would be working on or through a thickness X, and that temperature gradient would result in a heat transfer across the plate. Could be a wall, could be a door, could be a window, but you get a heat transfer rate. And that heat transfer rate is minus kappa times A dt dx, where Q dot is the heat transfer rate. It would be in units of kilojoules per second. Kappa is the thermal conductivity. That is a value that varies for each substance. Each substance may have a different, or will have a different kappa. The units for kappa would be in kilojoules per meter Kelvin second, or sometimes you'll see it as watts per meter Kelvin. Area is the cross-sectional area of the object, and dt dx is the temperature gradient. That is the difference in temperature divided by the distance, or we could say that that is delta t over delta x.